What started as a simple water level controller turned into a multi-year engineering project with 3 completely different sensing technologies. In this video, I'll show you how I went from basic metal rod sensors, to capacitive sensing, and finally to an air pressure-based system designed for extremely narrow wells where traditional float switches simply don't fit. You'll see what worked, what failed, the unexpected problems I encountered, and how artificial intelligence helped me build the final version of the controller and its software. Make sure to watch until the end, because the final prototype includes automatic hose cleaning, pressure-based water level measurement, fault detection, and code developed entirely with AI assistance. Let's start with prototype number 1. My first prototype was intentionally simple. It used 3 stainless steel rods inside the water tank. 2 long rods reached down to the low water level. 1 rod acted as ground, while the second rod was the low-level signal input. The third rod was shorter and positioned at the upper water level. The operating principle was simple: water conductivity. When the water touched the short upper rod and the ground rod, the controller detected a high water level and started the pump. As the pump emptied the tank, the water level dropped. When the water no longer touched the 2 long rods, the controller detected a low water condition and stopped the pump. This design was inexpensive, easy to build, and surprisingly reliable, but I wanted something that was less dependent on water conductivity and electrode contamination. That led to prototype number 2. For the second prototype, I moved away from direct electrical contact with the water. Instead, I used 2 electrically isolated metal rods. These rods formed a capacitor. As the water level changed, the capacitance between the rods changed as well. The controller continuously measured this capacitance and used it to determine the water level. Because the rods were insulated, there was no electrolysis and no direct electrical contact with the water. To improve safety, I added a float switch at the top of the tank. This float acted as an independent backup protection system. If anything went wrong with the capacitive measurement, the float switch could still prevent an overflow. This design worked extremely well. In fact, it operated continuously for about 2 years without interruption. But eventually I faced a new challenge. I needed a controller for a very narrow well pipe where neither a traditional float switch nor larger sensor assemblies would fit. That requirement led to prototype number 3. The third prototype uses a completely different approach. Instead of measuring conductivity or capacitance, it measures air pressure. A small silicone tube is placed inside the narrow well. The end of the tube is located near the pump intake. A small air pump periodically blows air through the tube. An air pressure sensor then measures the pressure required to push air out of the tube. Because water pressure increases with depth, the measured air pressure directly corresponds to the water level. This method works perfectly in very narrow pipes where conventional sensors cannot be installed. The system uses an Arduino Nano, a pressure sensor, a small air pump, an LCD display, and a custom control algorithm. The software measures the water level, starts and stops the pump automatically, cleans the sensing tube, and monitors the entire process. However, development was not always smooth. At one point the controller suddenly stopped working. I initially believed that the Arduino Nano had failed. After some troubleshooting, I discovered that the Arduino itself was perfectly fine. The actual problem was the 5-volt voltage regulator supplying the electronics. Replacing the regulator brought the system back to life. And that brings us to today's project. For today's version, I decided to do something completely different. The software for this controller was developed entirely with artificial intelligence assistance. Together we created a state machine-based controller capable of handling a wide range of operating conditions. The controller periodically cleans the pressure tube using the air pump. It performs filtered pressure measurements. It automatically starts pumping when the water level reaches the upper threshold. It stops pumping when the well is nearly empty. It monitors pump runtime. It detects abnormal operating conditions. It includes watchdog protection to recover from electrical interference generated by the pump. and it continuously displays operating information on the LCD screen. During development, we encountered several interesting software challenges. The watchdog timer caused unexpected resets because blocking delays were used. The display occasionally froze while measurements were running. State transitions created blank screens. Timing functions had to be rewritten using non-blocking millispace logic. Several display and runtime bugs had to be tracked down and corrected. Step by step, these problems were solved until the controller became stable and reliable. This project demonstrates how modern AI tools can accelerate development while still requiring testing, troubleshooting, and engineering judgment. If you enjoyed following the evolution of these 3 prototypes, check out my other electronics and Arduino projects on the channel. Don't forget to like this video, subscribe, and leave a comment about which prototype you found most interesting. Thanks for watching, and I'll see you in the next project.